Good day and welcome back for the fourth installment on Lagrange multipliers. In this example, we will combine our Lagrange multiplier material with the extreme value theorem we discussed in the previous section. So as a reminder to get us going, if we have a continuous function here of several variables on a closed and bounded set in R2, then f is guaranteed to have an absolute maximum and minimum value somewhere in D. And furthermore, those values occur at one of two types of points. So a critical point inside D or somewhere on the boundary or the outside of D. And this combines very nicely with our current topic. For example, let's see if we can find the extreme values of this continuous function of two variables on the region described to the right. And let's just think for a moment kind of what this region will look like. And manipulating our inequality, we see that we can write this as x squared plus y squared over 1/4 is less than or equal to 1. And if we think about where this is in fact equal to 1, we would have the equation of an ellipse as our boundary. So if we want to consider x squared plus y squared equals 1, that would be an ellipse which is a bit wider than it is tall. It intersects the horizontal axes at plus and minus 1 and the vertical axes at plus or minus 1/2. And as the inequality is x squared plus y squared over 1/4 is less than or equal to 1, that's describing the region enclosed by that boundary ellipse. So in terms of where we would find these extreme values, they occur at one or 2 points. A critical point somewhere inside, so we need to know or find the critical points of f, or along the boundary. And along the boundary is where this idea of using Lagrange multipliers will appear. So let's start right from the beginning. The first thing we need to do is locate the critical points. For the function f, which is e to the minus xy, the partial with respect to x using the chain rule is minus y e to the minus xy. And similar, the partial with respect to y, once again using the chain rule, is minus x e to the minus xy. And a critical point occurs precisely at a point of the form x comma y that simultaneously forces both of these first partials to be equal to 0. And it turns out that this is much simpler than it might appear at first glance, because recall when it comes to an exponential, such as e to the minus xy, exponentials are never equal to 0. So the only possible way these partials can be 0 is when y equals 0 for the partial with respect to x, and x equals 0 with the partial with respect to y. So we have a single critical point at 0, 0. And note, 0, 0 is right in the middle of our region. So this is a point where an extreme value could occur, so we need to evaluate the function at this critical point. And e to the 0 is 1. Now that we've determined the critical points inside the region, evaluated the function there, we've taken care of kind of this first potential location for critical points. The second is to now maximize and minimize the function f on the boundary. And notice what that is really asking us to do. We're suggesting that we want to maximize or minimize the function of two variables subject to the constraint given by g of xy equals x squared plus 4y squared when it is equal to 1. And as claimed, this is a Lagrange multiplier problem. So let's now find the extreme values on the boundary, and just keep in mind we will have to come back to this value at the critical point to compare with. So using Lagrange multipliers, we have our equations. The gradient f is lambda times the gradient of g, with that constraint equation. And remember, this is really three equations to deal with. We have the equations coming from the gradient. So f sub x, which we've calculated above, is equal to lambda times g sub x. And note, g sub x is simply 2x. Similarly, f sub y minus x e to the minus xy from above is lambda times g sub y, which is 8y. And then we also have our constraint equation. And remember the goal, I will repeat this every time. We want to work with these gradient equations until we have enough information to substitute into the constraint. And to get started, I want you all to make an observation. When we look at these first two equations, what specific quantity makes this appear to be difficult? And if you said e to the minus xy, I agree with that. So one thing we could do is maybe try to get that out of the picture. That is, if we start with the first equation, we can isolate that e to the minus xy. It would be lambda times 2x divided by minus y. And then we can go ahead and plug this in for e to the minus xy in the second equation with the hope of having something more reasonable to work with. So if we do that, we would now have x over y lambda 2x equals lambda multiplied by 8y, where we have immediately canceled off the two negative signs. And creating just a little bit more space to work, let's simplify this. We have a lambda times 2x squared on the left equals lambda times 8y squared on the right. And what all of our instinct is telling us is, how about we divide both sides by lambda? And similarly, how about we divide both sides by 2? So x squared is equal to 4y squared. Now, when we make this step of dividing both sides by lambda, there's an implicit underlying assumption we must be careful of. And that assumption is we're assuming lambda is not equal to 0. And in this case, there's no issues with that. We're not missing anything. And let me just kind of note why. If I was to make this assumption lambda is equal to 0, then our two gradient equations would become minus y e to the minus xy equals 0, minus x e to the minus xy equals 0, which should look familiar if you gander just a little bit above. That gives us x equals 0 and y equals 0. But in terms of working on the boundary with Lagrange multipliers, it's not possible for x and y to both be 0. So note, this is not possible, as x squared plus 4y squared must be equal to 1. So it is a perfectly reasonable assumption to assume lambda is not equal to 0. But I will caution you that there are examples where lambda equals 0 would give you potential points where an extreme value might occur. Just not in this case. So back to our original work. By rewriting e to the minus xy, substituting into the second equation, we found that x squared is equal to 4y squared. Now we are ready for the constraint equation. So going to our constraint equation, we can replace that x squared with a 4y squared. So 8y squared equals 1, which means y squared is 1/8. One step further, this means y is plus or minus the square root of 1/8. And note that we do need to get the corresponding x values, which we get by going back to our equation involving x's. So if we combine those two steps, we would find x squared is 4y squared, so 1/8, which means x squared is 1/2, or plus or minus the square root of 1/2. And this gives us 4 more potential points where we can have extreme values occur. And what we need to do is evaluate our function at each of those 4 points. So if x is positive the square root of 1/2, it is possible that y is plus or minus the square root of 1/8. And then similarly with the negative square root of 1/2 for x, y can be positive the square root of 1/8 or negative the square root of 1/8. And if we evaluate our function f at each of these, we would get e to the minus 1/4 for the first and last possibility, and e to the positive 1/4 in the middle 2 cases. And the last thing we need to do is look at our list of potential outputs corresponding to these extreme values. We have from above, as a reminder, at the critical point, the value of the function is 1. So I'm going to go ahead and just add that to our list below so we can more easily compare. And of these 3 potential numbers, I'm going to say the biggest value would be e to the 1/4, and the smallest value would be e to the minus 1/4. And a simple graph will maybe make that observation a bit more clear. If we were to investigate the graph of y equals e to the x, it is an increasing function, and it crosses that y-axis precisely at 1. So if we were to substitute in the value minus 1/4 or 1/4, we could trace up to the curve and then over to the y-axis to see that e to the 1/4 is bigger than 1, and e to the minus 1/4 is smaller than 1. So this graph is showing us that e to the minus 1/4 is less than e to the 0, which is 1, is less than e to the 1/4. So we have our minimum value associated with e to the minus 1/4 and our maximum value associated with e to the positive 1/4. And I'll circle those corresponding outputs as our final answer, which completes this current example. So make sure to remember the takeaway that we can combine together the extreme value theorem and use Lagrange multipliers on the boundary. Something to be on the lookout for. In our next video, we will investigate one more example dealing with Lagrange multipliers. So stay tuned and take care.